Greetings, everyone. This is the group from Kyushu Institute of Technology in Japan, and our project is called Hermes CubeSat, on-site data gathering for accurate mapping of the main asteroid belt. First, we'll introduce you the motivation that drove us to make this project. Then we will introduce the mission objectives, the concept of operations, how the CubeSat is designed, and how we plan to implement this project in the future. So it is no secret that there has been a shift in space accessibility, and this shift has enabled developing countries to access low Earth orbit. And the key advances to this shift have been technology miniaturization, energy efficiency, and power capabilities. So we have transitioned to bulky satellites to CubeSats with off-the-shelf components. And we believe that the next step after democratization of LEO is the democratization of deep space. Our vision is a world where, through technological innovations and with the right companies willing to put in the resources, asteroid mining is viable. We know that currently it's not it doesn't make economic sense, but our goal is that once it's economically viable, provide an extensive database for asteroids to those companies. Why do we want to go there? Basically, the ground observations for asteroids are not 100% reliable. Notorious examples are the Ryugu asteroid, where they thought it was a compact asteroid, and it turned out to be a pile of rubble, and the Ultima Thule asteroid, where they thought it was spherical, and it turned out to be mostly flat. Also, the current numbers for asteroid population are based on indirect estimations, such as extrapolation methods and reading on the surface on the moon of moons. How do we plan to go there? This is our proposal is a flat 9U CubeSat with a deep space network capabilities, and these are the constraints that were given by the organization. And our trajectory will be a highly elliptical orbit around the sun without one impulse trajectory from the Earth, and we define three phases: communication, operation, and standby. And these phases will be explained later on.
Mission objectives now aim to describe more about the technical solutions and the orbital aspects. Radar detection is the key phase of this mission, since we want to make a flyby and send a radar signal in various directions for collecting information about Doppler effect, time delay, or magnitude. We can have this information in a reflected signal, obviously, which can give us information about the relative velocity, the distance of these objects, and their average size and shapes. This radar is inspired from the RainCube mission's deployable radar, which is not commercially available because under development, but can deploy from a 1.5 unit in volume to 2.5 unit, which makes it very small and lightweight. And by using amplifier and converter, we can convert the signal for it to be sent to Earth using antennas. Here in table 2, you have some figures about the raw data we can send to Earth, which is not treated. As you can see, the quantity of data is really important, and the duration of communication is 156 days, which will result in a great cost for this communication. So we will need to decrease this amount with an onboard treatment of void suppression and compression. Now, concept of operation is more for describing the orbital aspects of the mission. We don't have any precise frontier for the main belt. So what we want to know is where we want to go, because as you can see on these graphs, we have a greater density of objects between 1.7 and 4.4 units from the sun. So we want to target the beginning of this area, which is around 2 units from the sun. The flyby zone here is a corridor between 2.2 units and 2.24 units, which we are going to stay in for 100 days, which is the duration of the flyby, following this highly elliptical orbit. The required delta V for such maneuver is between 5.14 and 5.20 kilometers per second, which is achievable with standard rockets.
Mission objectives and concept of operation has been described. In this part, the choice of a CubeSat architecture will be discussed. So as you might know, CubeSat is a technology that has been developed in 1999 by universities to launch small satellites at a lower cost. However, over the past 20 years, more and more tech companies and space agencies have been using them for various missions. And this has resulted in an exponential growth of CubeSat launches over the past few years, as you can see on the right graph. If you take a look at the left graph, you can see that just this year in 2021, over 750 CubeSat are expected to be launched. Now, CubeSat are usually used for low Earth orbit, but some of them went to deep space. For instance, NASA's Mars Cube-1 mission or the European Space Agency APEX missions. And this rise of the use of CubeSat for deep space explorations is what comforts us in our architecture choice. Now, since our mission is university scaled, the cost of development was a determining factor. And this is granted by the use of off-the-shelf components, which allow cost reductions. But we also thought about development time, that we needed quick. And the standardizations of off-the-shelf components allow us for repeatability and availability of the components. Meaning that if the need of another CubeSat for exploring a different part of the main asteroid belt were to rise, we believe that with this architecture, we would be able to provide it. Now, off-the-shelf components have some drawbacks, of course. One of the main is the lack of diversified scientific equipment. And to tackle this issue, we thought about modifying some components for needs. For instance, the use of a star tracker could be for asteroid observations in parallel with the antenna. And while we would have the quick and fast development time, cost reduction, and repeatability of off-the-shelf component, we wanted to make sure to still have some room for modification if the need were to rise in the future.
Now I will speak about the part 5, the implementation plan. Regarding the total life cycle cost of our mission, we based ourselves on the few existing deep space CubeSat projects, such as Marco, Mars Cube-1, a nanosat dedicated to Mars mapping. In this total life cycle cost table, we have included the main concepts, from the design, development, component assembly, integration, testing, launch, and operation into the main belt. However, we had to increase the cost of some of these concepts because we will be using mainly off-the-shelf components that require modification to adapt them in our mission context. So at the end, we obtain an allocated budget around $35 million. All the operation related to the assembly and test will take place on the same facility at the campus of Kyushu Institute of Technology in the Lassen laboratory. The main purpose of keeping the same location for every development phase is to reduce the development time, the cost, and to minimize the mission risk factor. About the project organization, the workload will be divided into several groups of people. So in that way, all the tasks will be carried out efficiently in parallel with each other. So in concrete terms, it's a total of 32 people divided into 7 teams: mechanical team, thermal team, solar array team, onboard computer team, orbit and altitude control team, management, and payload. As part of this project, scientists and engineers will be encouraged to work together in order to ensure that the spacecraft will be able to meet all its mission requirements. On top of that, monthly meeting between the supervisor of both the scientific and engineering teams will enable to prevent any change in the nature of the mission. This Gantt diagram represents our project schedule. So it has been set to start in the beginning of the year 2022. This figure is a top-level project schedule that gathers all the main activities and their duration, which are involved in the development of our mission. For making it, we tried to maximize the team collaboration while minimizing the development time. The total expected duration is 1,400 days, which corresponds to almost 4 years.
As a conclusion, if the mapping of the main belt leads to a better understanding of our own solar system, the Hermes mission aims to be the messenger for future deep space mission by proving we can use onboard radars for deep space observation at a lower cost. Some solutions have been suggested to allow satellites to gather and to communicate information to Earth at an acceptable cost. However, the orbit of the mission forces the satellite to have a great heat and radiation protection, which obviously decrease the lifespan of the satellite. Yet, these 100 days of communication and observation will lead to the creation of a great data bank of various subjects in the solar system. Thank you for your attention.